So the plan for today is we just finish the remaining practice questions for chapter 2. Okay, we have around 5 left. Okay, so no need to rush. So last time we stopped at question number 6, I think on page 68. Okay, so I think that's worth to repeat. Okay, so in that questions, we're trying to select 3 professors from totally 10 professors, and then we assign a department head, assistant department head, and faculty senate. Okay, faculty senate. So in these questions, we have several different ways to make it correct. Okay, so you can think this as a permutation question. Okay, so one step you can figure out the answer. Okay, it may be hard for you to understand why it is permutation questions. Okay, so remember when order does matter, we should use permutation. Okay, so we choose 3 professors from the 10 total. Okay, we choose 3 from 10, and the 3 chosen has different roles. Okay, head, associate head, representative. Okay, and because of that, the order will be matter. Okay, so if you notice, you can just directly use permutation. That will be P310. Okay, and you get answer. Okay, or you can use method number 2. Always think carefully how this experiment is done, by which steps. Okay, you can think this experiment is composed of 2 steps. One is we choose 3 professors from the 10 total. Okay, so just choose 3 from the 10 total. That will be a combination question. Okay, because the order does not matter. We choose 3 from the 10, so that will be C310. Okay, and then we assign these 3 chosen professors into 3 different positions: head, associate head, and representative. So the second step, will be assign 3 professors to 3 different positions. Okay, so that will be P33, or 3 times 2 times 1. Okay, the first step we choose 1 professor for the first position, and then we choose 1 professor from the remaining 2 for the second position, and then remaining 1 will be for the last position. So that is 3 times 2 times 1. Okay, so that's method number 2. You can think that way. Okay, or you can think like in the method number 3. We think this experiment as 3 steps. So the first step is we choose 1 professor from the 10 total professors for the department head position. Okay, so we have 10 choices. The second step will be we choose 1 professor from the remaining 9 professors, because 1 is already chosen. Okay, for associate department head, so we have 9 choices. And the third step is we choose 1 from the remaining 8. Okay, because we chosen 2 already. Remaining 8 professors for Senate representative position. Okay, so that's 8. So 10 times 9 times 8, we get 720. Okay, all the 3 methods you will get the same answer. Okay. Okay. So if you don't have any questions, let's continue for question number 8. Question number 8. Okay. So we have a license plate in a certain state consists of 3 letters. Okay, A, B, C, D, E, okay, until Z. So 3 letters followed by 3 digits could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Question part A, how many different license plates can be made? Okay, so let's see this license plate have 3 letters. Let's see, letter 1, letter 2, letter 3. Okay, and 3 digits. Okay, let's see, D1, D2, D3. Okay, so how you can assign numbers and digit letters to this license plate? How many ways we can do that? Okay, so we can think this as 6 steps. Okay, the first step, we assign a letter to letter number 1. Okay, so how many letters we have? We can choose. So from A to Z, we have 26, right? So we have 26 choices. Okay, so the first step, letter 1, we have 26 choice. For letter 2, how many choices we have? So we choose a letter for the second position, letter 2. So how many choices we have? Is it 25?
26.
26. Okay, yeah, it is 26 because it didn't say we cannot repeat the same letter in letter 1. So again, we have 26 choice for letter 2. So step 1, 26 times step 2, 26. Okay, and then you got it. Step 3 will again be 26. Okay, and then the fourth position will be a digit. So digit 1, D1, how many choices we have? Okay, we have 0, 1, 2, 3, 9. Okay, so we have 10 choice. Okay, so we can choose one from the 10 digit. Okay, that's D1. That is step number 4. Times step number 5, again, 10 digit, times the last step, 10 digit. Okay. All right. This is how many different ways, different choices we can make a license plate. Okay, so that's part A. All right. Part B. How many license plates are there that contains neither the letter Q or nor the digit 9? Okay, so we cannot use Q or 9 in that. Okay, so again, for the 6 different steps, so because we cannot choose Q, we only have 25 choices, okay, for the letter 1. So that is 25. Okay. Again, letter 2 cannot choose Q, 25 times 25. For the digit, we cannot use 9, so we have only 9 choices. Okay, 0, 1, 2, 3, 4, 5, 6, 8, 10. Okay, so 9 choices times 9, then times 9 times 9. Okay, so simple enough. So 11,390,625. Okay, so that's part B. Part C is asking, a license plate is drawn at random. What is probability that it contains neither Q nor the digit 9? Okay, so how to answer that part of question? So what is probability that contain no Q and no 9? Okay, so to calculate the probability for that, we should know how many, in total, how many ways we can design a license plate. Okay, so that part of answer is already given us from part A. Okay, so in total we have this much, this many, 7,576,000 ways to make license plate. Okay, contains no Q or 9. Okay, so how many ways we can make? So that is part B. Okay, right? So part B is asking how many ways can make license plate with neither Q nor 9. Okay, so that is 11,390,625. Okay, so the probability license plate drawn at random has no Q nor 9 will be the ratio of this. Okay. 6481. All right, so question about this part.
I'm sorry, but I have a question going all the way back to part E.
Part E.
I mean A, excuse me. I understand how we got the figure for 26 for L1, L2, and L3. But
Yes.
how did we determine that there was only 10 options for the numbers?
Numbers, the digit, single digit, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's a single digit. Okay.
Okay.
The single digit, you only have 10 choice from 0 to 9. Okay, that's 10.
I see.
Choice.
I see.
All right. Okay. Any other questions? Let's see.
And then
Yes.
I guess it's just more of like a word problem skill set, but when it says the 3 digits, that means that each one of the numbers has to be a single digit, correct?
Yes. For the license plate, I think Hawaii has like that, right? License plate, 3 letters and 3 digits. Okay. So
I see.
yeah.
And then, so A and B are pretty straightforward, and C is a permutation problem or a probability problem? I see a P that's right.
C is the probability. P is for probability, is not for permutation, right? So asking the probability contains neither Q nor 9. So from part A, we know the total number of choice for all the license plate is 17 million. Yeah. Okay. So, and we have 11,390,625 choices for license plate has neither Q nor 9. Okay, so that's the ratio of these two numbers give us the probability.
I see.
Okay, yeah. Because every single license plate are equally likely events. They have the same chance. Okay, so one has, each license plate has this much of chance for each license plate. Okay.
Just out of is there a way that you could express this equation with the union or the and or notation?
No, it's not union or nor and on all. Okay, so
Okay.
yeah.
I was just curious if there was a way to express this.
In that way.
Yeah, in that form.
No. Yeah, this is like a experiment. You think that experiment into different steps. And then for each step, you figure out how many ways to do that. Okay. Okay. Yeah. All right, that's question number 8. Let's continue. Page 159. One 59. Here. Right. First one is question number 2.
We're in section 2.3 now.
Let me see. Oh, no, 2.3. It's a supplementary exercise for chapter 2. So that's including all the sections.
So that would include conditional probability, random variables,
yeah, some of them.
linear functions of random variables, and jointly distributed random variables.
Jointly distributed, we don't have the question for that. Okay, that's pretty complicated. But for now, you focus on the early sections, not like a 2.6. Okay.
Okay.
There's page 159. Hold on. Where is it?
Oh, so this is the supplementary exercises for chapter 2.
Yeah, that's here. Okay, here. All right, I got that page. 159, question number 2. All right, that's about the old toss a coin question. Okay. So a fair coin is tossed until a head appears. Okay. A coin could have head or tail. And for fair coin, the chance has a head is 50%. So does the tail. Okay. So what is probability that more than 3 tosses are necessary? Okay. So what is probability? That's question number 2. More than 3 tosses are necessary. Okay, so let's see what the question is trying to do. The question is trying to do, the experiment trying to toss a coin until a head shows up. Okay, so when more than 3 tosses are necessary, means what? So in what situation we need more than 3 tosses? The experiment will stop as soon as a head shows up. So if more than 3 tosses are necessary, that tells us the first toss is tail. The second toss is also tail. And third tail is also a tail. So only when the first 3 tosses are all tails, then we need more than 3 tosses. So if you realize that, then you can figure out the question easily. Okay, so more than 3 tosses necessary. In this experiment, we try to get a tail, get a head, sorry. So that will be equal to the probability the first 3 tosses are all tail. All tails. Okay. So what is probability the first 3 tosses are all tails? Okay. Using counting method. Okay.
This is a counting method problem?
Yeah, counting method. The first step, second step, and third step. Okay. So the first step is first toss. Okay. We're trying to figure out the first 3 tosses are all tail. So the first step is the chance we get a tail. Okay. P tail 50%. The second toys also get a tail. It's also 50%. And so does the third. So okay. So that is 1/8 chance. Okay. So more than 3 tosses are necessary in this experiment. That means the first 3 tosses are all tail. Okay. So if you know that, using counting method, you can calculate the probability. Okay. Questions for this?
From chapter 2.2 in counting methods, can you reference which example that we could refer to?
Which example? I cannot remember which example we discussed. The only, just for each question, they will be different. Okay. So the easiest way is to think carefully how many steps to fulfill, to realize that experiment. Okay. And how to make it an easier calculation. Okay. And I think you need some practice to get familiar with this counting method. Okay. Sometimes you can directly use a combination or permutation, but not always. Okay. Yeah, but not always.
I'm trying to find it right now, but I just know that in section 2.2, they have like about 6 or 7 different examples, and each example is kind of different from the other one. And so I was just trying to find which one would kind of give a better way to set the problem up.
Yeah. I don't remember the examples, but you're welcome to stay after the class. We can have some discussion if you like. I have a class after this, but you have some specific questions, you're welcome to join the meeting with me. Okay. So for now, let's continue. It is question number 2. So question number 4. Okay, so question number 4 showing us again the intersection conditional probability, okay, and how to use the Venn diagram to figure out the question. So let's read question together.
So this is number 4 is a conditional probability.
Yeah, some
problem.
Yeah, some part.
And using a Venn diagram.
Yeah, the Venn diagram will be helpful. Some of you may not think that's necessary. Okay, it's depending on how you, what I mean is that there are different ways to figure out a certain question. Okay, 2 production lines are used to pack sugar into 5 kilogram bags. Okay. So line 1 produces twice as many bags as does line 2. 1% bags from line 1 are defective, and 3% of bags from line 2 are defective. 1 bag is randomly chosen for inspection. So part A is asking what is probability that it comes from line 1. Okay, so let's do some definition. So first of all, let's define D. D means defective. Okay. D means the bag defective. Okay. And let's define L1 as line 1. L1, so bag from line 1. And L2, bags from line 2. Okay. And then the question tells us what? Question tells us 1% bags from line 1 are defective. Okay, so that means the probability the bag is defective when it is coming from line 1. So that is given. So again, this straight line means given, conditional. Okay, so under the condition, it coming from line 1, then the defective percentage is 1%. So question tells us this. So that is 1%. Question also tells us 3% of the bags from line 2 are defective. So that is P defective given under the condition coming from line 2. So that is 3/100. Okay. So if we use a Venn diagram, let's draw something. Okay, so let's say this is line 1, this is line 2. And let's use a circle to represent it is defective. Okay. Okay. Part A is what is probability that it coming from line 1? Okay, random bag is chosen for inspection. The probability is coming from line 1. Okay, so on the second sentence, question tells us the line 1 produce twice as many bags as does line 2. Okay, so if line 2 produce 100 bags, line 1 will produce 200 bags. So out of this total 300 bags, 100 coming from line 1, line 2, 200 coming from line 1. Okay, then what is answer for A? What is randomly chosen bag coming from line 1? So that part is very straightforward, right? So depending on the number of bags produced.
So that would be 0.001, right?
0.00, no, the probability is coming from line 1. No, 0.001 is, if it's coming from line 1, what is percentage is defective? A is not asking for defective. It's just asking for a randomly chosen bag. It is coming from line 1.
Oh,
Yeah. Okay. Yeah. Okay. So somebody answer that question from the chat. Okay. So if line 2 produce 100 bags, line 1 will produce 200 bags. So out of these total 300 bags, 200 will coming from line 1. So for part A will be 2/3. Okay, so that is the probability is coming from line 1. Okay, so part A is okay. Let's look at part B. Part B, what is probability that it is defective? Okay, so because we define that circle is defective, okay, so basically it's asking the probability in that circle. Okay, so B is probability it is defective. Okay. So that is equal to two parts added together. Okay, so which two parts? Okay, so this is probability is defective and is coming from line 1, which is here, right? Because the circle is defective, line 1 is here, so this area, right, will be is PD and L1, the intersection of L1 and D, correct? Okay, plus PD and L2, which will be this half or almost half circle. This part is the probability is defective and coming from D2. So that is the intersection from D and L2. Okay, so question for this. And how to figure out that part? We can use the conditional probability. Okay, so under conditional probability, the first part will be equal to okay, PD given L1 times PL1. Okay, so that is the probability is defective given it is coming from line 1 times PL1. Okay, so again, this part is equal to this part. So that is the definition of conditional probability. Question for this. And
I was just trying to remember that
yeah,
is and, right? And
yeah, and half circle facing down is and. You know, you need to do more practice. So whenever you saw that, you know it's and. You know, just you know, yeah, you just need more practice. Okay. and the line is given, conditional. Okay. And based on the conditional probability, this part is equal to that part. And you should know that too. Okay. Okay. And that will be equal to 1/100 times
3/100.
2/3. Okay. Then let's deal with the second part here. So PD and L2, that is
Oh, that's
equal to
2/3. That's
P,
fine. Okay.
PD given L2 times PL2. Okay. So PD given L2, 3%. PL2, okay. PL2 is 1/3, correct? Because PL1 is 2/3, so PL2 will be 1 minus PL1 will be 1/3. Okay. Again, as I said, PD and L1 is equal to PD L1 times P L1. Okay, so that is based on the conditional probability. Oh, let me make it. And L1. Okay, so it is because based on conditional probability, okay, this is true. Okay, the same format. You just move the PL1 to the other side. You get this. So this is the equation for conditional probability. Okay, and based on a Venn diagram, you know which part is PL1, right? PL1 is this 2/3, okay? And you know the PD and L1 is the intersection between L1 and D, and so on. Okay. So the answer for PD is 1/60. Okay, so this part could be a little confusing at the beginning. Okay. All right. Let's continue for part C. For part C, if the bag is defective, okay, so that is another condition. We know a bag is defective. Okay. Asking what is the probability that is coming from line 1. Okay. So part C is asking this. Okay. So if it is defective coming from line 1, okay, that part. Again, based on the equation for conditional probability, that is equal to this. Okay, so that is equal to PD given L1 times PL1. Okay, so this part is equal to PD and L1. Okay, from the Venn diagram, PD and L1 will be this area. This area. Okay. So this area over PD. And PD is what? PD is just the whole circle of D. Okay. So that is conditional property. P L1 given D means under the condition of D within the circle of D, what is the properties coming from line 1? Okay. And all the three.
Wait a second.
Questions?
I'm sorry, I can't see the bottom of that equation. Could you scroll up just a little bit? Oh, okay. So that's P times D or, no, B and L1. And L1.
And, yeah, half circle facing down, that's and.
Okay.
And, okay. And the question tells us about all of this. For example, PD given L1, that is 1%. PL1 is 2/3. And PD is 1/60. 1/60. So the answer is 40%, 2/5. Okay. Let's continue. Part D. So part D is asking if the bag is not defective. Okay. So not defective means outside that circle of D, outside that yellow circle. If it's not defective, asking the probability that is coming from line 1. Okay. Then which part this question is asking? Okay. If it's not defective, that means the outside that circle, that's the condition. So within outside the circle, what is property is coming from line 1? It is this shaded area over all areas outside D. Okay, then let's do it. So the question is asking P L1 not defective. Not defective means this. So given DC, so C means complement or not D. So not D means not defective.
Is this a Bayes rule problem?
Bayes rule.
Is this a Bayes rule application?
Yeah, let me double check that on that. Okay. This is the conditional probability. Okay. Yeah, Bayes rule is talking about exhaustive and exclusive. So yeah, I think let's say under this condition, L1, L2 are exhaustive and exclusive condition events. Okay. So PL1 given complement of D, not D. Okay. So basically we use the same equation in part C. That is this. Okay. The part on the top, okay. So this part is equal to PDC and L1, okay, and L1. So again, this is this area, the yellow area. Outside D, outside the circle of D, and belong to L1, or the intersection between L1 and DC. Okay, that's the top part. Okay, the bottom part, PDC, is just the whole area outside D, the whole yellow area here. PDC is easier, okay, because that is equal to 1 minus PD. Okay, PD is 1 over 60. Okay, so PDC, the bottom part is easy. The top part, okay, is equal to given it is coming from L1, the property is coming from, it is not defective. Okay, so that part is equal to 1 minus PD given L1. Okay, and PD given L1, sorry, PD given L1 is 1 over 100. Okay, so that will become 1 minus 1 over 100 times PL1, 2 over 3. The bottom is 1 minus 60, 160, 1 over 60. Okay. So this question shows us how to use conditional probability to figure out the answer. Okay. If you feel like you use Venn diagram to help you understand, that is fine. Okay. If you are very comfortable to use equation for the conditional probability, okay, that's okay too. Yeah. It may take some for you to fully digest the concept, the idea of what is conditional probability, what is intersection combination, and what is, yeah, and so on. Okay. Again, this is question number 4. Next, question number 6. Okay. So question number 6, this is about counting method, showing us an experiment. We'll figure out what are the steps, how many choices for each steps. Okay. So in certain type of automobile engine, cylinder has fastened to the block by 10 bolts. Okay. Each of these 10 bolts should be torqued to 60 Newton meter. So Newton meter is the unit of torque. Okay, torque. How much force torque you use. You tighten the bolts. Okay. Assume that the torques of the bolts are independent. Okay. A, if each bolt is torqued correctly with probability of 99%, what is probability that all the bolts on the cylinder head are torqued correctly? Okay, so the engine has 10 bolts. Okay, for each bolt, the chance it is torqued correctly is 99%. Asking the probability all bolts or 10 bolts torque correctly. Okay. The question tells us each of these 10 bolts are work independently. Okay, so we can think this experiment as 10 steps. Okay, the first step is we torque the first bolt. We have 99%, we get it correct. Then the second step is the second bolt, 99%, we get it correctly. Okay, and so on, third, fourth, until the 10th bolts. Okay, so for first part, all bolts torqued correctly will simply be 99% to the power of 10. Okay. So we have around 90% chance we torque all the 10 bolts correctly. Part B, that's A. Part B, if the goal is for 95% of the engine to have all bolts torqued correctly, what must be the probability that a bolt is torqued correctly in order to reach this goal? Okay. So the question is telling us we want the probability all 10 bolts torqued correctly to be 95%. .95. Okay, and we try to find for each bolt what should be the percentage be torqued correctly. Okay, and from part A we know if for each bolt 99% torqued correctly, we only get 90% for all the 10 bolts. Okay, so the question will become what should be the probability for each bolt torqued correctly to the power of 10 equal to 0.95. Okay, we're resolving for this question. So P should be 0.9949%, 0.9949. Okay. So that is question number 6. Questions? All right. Okay, we're almost there. We have one more questions. Question number 8. So here, give us the probability density function. Okay, so we know we're gonna do some integration work. Okay. So the reading given by a thermometer calibrated in ice water. Okay. The actual temperature of ice water is 0 degrees Celsius. Is the random variables with probability density function of this. Okay, fx equal to k, blah, blah. So the range for x is between -1 to 1. Outside it is 0. So probability density function. Okay, and k is a constant. A asks us to find out the value of k. So how to find out the value of k? Okay. So one nature of probability density function is what? For probability, if we add all the possible outcome together, it will equal to what? So we mentioned this during class at least 3 or more times. Okay. Remember, for the density function, if you do the integration for all the curve over the whole range, the areas will equal to 1 or 100%. Okay, that makes sense because the whole probability will equal to 100%. No more, no less. And based on this nature, we can resolve k. Okay, so because the density function only varied from -1 to 1. Okay, so if we do the integration for the PDF, okay, that should be equal to 1. Okay, so based on that, so k dx equal to 1. Okay. This part will become x minus x to the power of 3 over 3 from -1 to 1. Okay, equal to 1. Okay, so we resolve k 0.71. Okay, remember the whole areas underneath the density function equal to 1. For discrete variables, we add the probability all together. That's the sum for discrete variables, also equal to 1. Okay, so always remember that nature. So part B, that's A. Part B, what is probability that the thermometer reads above 0 degree? Okay, above 0 degree. Okay. The probability will be, we do the integration for the density function. The k is 0.75. So this is the density function, dx, okay, from 0 to 1. Question asking about 0 degrees Celsius. Okay. So we do the integration from 0 to 1. So that is 50%. C, what is probability that the reading is within 0.25 degrees Celsius of the actual temperature. So within 0.25 degrees Celsius. So could be no more than plus 0.25 or no less than minus 0.25 degree. Okay, so the range will be minus 0.25 to positive 0.25. Again, fx dx. This is fx dx. Okay. Right. So similarly, we get answer 36.7% chance. Okay. D is asking the mean value. Okay, the mean value based on the equation of mean. For PDF, the mean value will be x fx dx. Okay, so the range is -1 to 1. Okay, x fx dx. Okay. So the mean value, I will just skip the details. You do the integration. The mean value is 0. E, what is the median reading? Okay. To find the median we call that xm. M is for median. Okay. We need to resolve the equation okay, from -1, which is the lowest possible value, okay, fx dx, okay, so that area should be equal to 50%, 0.5. So that's the definition of median. Okay, so resolve for this equation, the only unknown is xm. Or minus 1 to xm equal to 0.5. Okay. So xm turned out to be 0. So the median is 0. Last part of the last question, F. Standard deviation. Okay, standard deviation is sigma. Okay. First of all, let's figure out what is sigma square. The name for sigma square is the variance. Okay, so we have two equations to figure out the variance. Okay, so either one is fine as long as you choose the easier one. Okay, so this is one of the equation for variance. Mu square. Okay. So the range is -1 to 1 x squared times fx dx minus mu. Mu is 0 here. Okay, 0 squared. So the variance variance turned out to be 0.2. Okay, but the question is asked for standard deviation sigma. So sigma will be square root of 0.2. Okay, that's the end for our first practice sessions for chapter 1 and 2. Okay. Questions?